Good morning, guys. Today our class is on binary operations. This is a part of the relations and functions chapter. So before learning about the binary operations, you should be familiar with a few terms. One is what relations are, what functions are, the idea of domain as well as range. Okay. So I am taking it for granted that my students know all of these concepts before moving on to the concept of binary operations. Let me start with the term binary. So what do you mean by binary? Binary means two. So basically binary operations are operations that involve two elements. So when I say two elements, they can be, mostly we deal with numbers. Now, which are the common binary operations that you have so far come across? The first one, the first binary operations that we learn about is addition. Then we learn about subtraction, multiplication and division. These are all binary operations because at any point of time we are dealing only with two elements. Even if we are adding three numbers, suppose I am adding 36 plus 18 plus 93, random three numbers, at any point of time I am adding, even if I am adding in this way 6 plus 8. So at a point of time I am adding only two numbers. So my addition is basically a binary operation. Same is the case with subtraction, multiplication or division. So binary operations basically cover, or when I say binary operations, you have to immediately understand that it is an operation involving two terms or two elements, right? Since under this particular concept of binary operations, we are dealing with numbers. I said binary operations deal with two numbers. So let me represent those two numbers by a comma b. These are two random numbers on which I am applying my binary operations. That binary operation can be addition, multiplication, subtraction, division or any other operation that I want to apply on two numbers. So can you think of any other operation that I can apply on two numbers? It can be, for example, I can find out the LCM of these two numbers, HCF of these two numbers. So I am applying a random operation which is called as a binary operation on any two numbers which is represented by a comma b. Okay. Now this a comma b can belong to the set of integers, the set of natural numbers, the set of real numbers or set of complex numbers, so on and so forth. Right? Let me represent any of these sets by a general term x. So the two elements a and b on which I am applying the binary operation belongs to a general set x. Okay, so that is the beginning of our definition of binary operation. Now, binary operation is normally represented by kind of a flower sign. Okay, so when I say a, binary b, this is how we represent it. I can also use other symbols. A few other symbols that are used is something like this. And O, it basically, so they will say it is a binary. It's a binary operation of a and b. So it is represented as a binary b. Okay. Now, and so when I say a binary b, I have to read through to understand that binary operation which I am mentioning is an addition, subtraction or whichever operation that I am going to define for a and b. A belongs to x and b belongs to x. Right? Now, if I am putting a and b in the set form, a comma b within the brackets, I can say that a comma b belongs to x because a comma b is a set. It looks like a Cartesian product. So that Cartesian product has to belong to the Cartesian product of x with x. Right? So the start of our definition of binary operation says that binary operation is applied on two elements a and b. When I am representing it as a set, a and b should belong to my random set x comma x, Cartesian product of x and x. X is a general set that can represent any of the set integer, real numbers, natural numbers, positive integers, anything. So depending upon the definition that is given for you, you have to understand my binary operation can be any operation that involves two elements like addition, multiplication, subtraction or division, and the element on which I am defining binary operation belongs to the Cartesian product of x into x. Okay. Now, one condition of binary operation is that the result of a binary b also should belong to x. For example, suppose I am defining a binary operation between a and b as addition of a and b. And I am telling you that a and b belongs to the Cartesian product of integers. Right? So I have to understand that a belongs to integer and b belongs to integer. So the addition of a and b should give me a value or a number that should belong to integers itself. That is the condition for an operation to be binary. Basically means whatever operation I am doing on two elements a and b should yield me a number that belongs to the same set that is defined for a and b. So if a and b belongs to natural numbers, the binary operation that I am doing on a and b should give me a number that belongs to the same natural numbers. If it doesn't belong to natural numbers, then that operation which I have called as a binary operation is wrong. That operation cannot be a binary operation. So let us see an example of a binary or of an operation that cannot be a binary operation, so that you get a clear understanding of what can be a binary operation and what cannot be a binary operation. Okay. Let me define a binary operation. I am defining a binary operation on a and b. I am telling that a and b belongs to the set of natural numbers. And I am defining binary b as a binary b is b minus a. I want to see if this is a binary operation or not. Okay. So, according to the conditions that I have laid down so far, let me see whether this is a binary operation or not. There is one more step that you need to check whether this is a binary operation or whether any operation is a binary operation. But I will come to that. Let me just see whether this is a binary operation according to what I said. Now, a and b belongs to natural numbers and they are defining I am defining a binary b as b minus a. So, the result of b minus a should always also belong to natural numbers. Correct. But do the result of b minus a always belong to natural numbers? What if b is less than a? If b is less than a, or if b is equal to 2 and a is equal to 4, b minus a will not belong to natural numbers. It will belong to integers. So, this particular operation which I mentioned under natural numbers is not a binary operation. How do I make it a binary operation? I make it a binary operation by redefining the set to which a and b belong to. So, I say that the set AB belongs to the Cartesian product of integers. In that case, b minus a, whichever be the value or whatever be the value of a and b, this particular binary operation which I defined by b minus a will belong to integers always. So, this will become a binary operation according to my definition. Right? Okay. Now, let us move on to the next condition under which an operation becomes a binary operation. Okay. So, what is it so far we have learned? A binary operation involves two elements which is normally represented as a Cartesian product. Now, second thing, the result of the operation should also belong to the set under which these two elements belong. If A and B belong to a particular set X, binary X, Cartesian product of X, then the result or the result of the binary operation of A and B should also belong to this particular X, whatever be the X is, integers, natural numbers, real numbers, anything. Okay. Now, what is the third condition for an operation to be binary? This binary operation which I am defining should be a function. What do you mean by a function? A function is a relation between two sets which are represented by domain and range, and every single element in domain has only one unique image in the other set. Correct? So, for an operation to be binary, that particular operation has to qualify under function. So, can you tell me an example of an operation that does not become a binary operation under this condition? Let us take the example of the binary operation between a comma b, I will take it as a and b belonging to the set of integers. Okay, so I will say a binary b is defined in such a way that b is the square root of a. Now you know that here you have got all the integers from minus infinity to plus infinity. Okay, so minus 100, minus 1, 0, 1, everything is here. Here also you have the same set. Plus 1. Right? Now if b is the square root of a, suppose I have got a number a as a minus 1. What is the square root of a? The square root of a will be square root of minus 1, which is I, which we have already learned about complex numbers which do not belong to this particular set. Correct? Or I can say that if I have, another reason is because if I have a 1, I will have 2 rows, minus 1 and plus 1. So again, it stops being a function. So this particular operation, b is equal to square root of a, is not a binary operation. On R, a binary b is equal to ab square. I have taken this sum from the NCERT textbook. So let us see whether this is a binary operation or not. So you know that on R, which means on real numbers, a and b is given, a binary is given as ab square. So a and b belongs to R. So we need to see whether ab square has a unique image in the range which is in R. So we need to know ab square has a unique image and whether that every unique image also belongs to R itself. So you know that whatever be the value of a and whatever be the value of b, a into b square has got only one value which is a unique image. Now that a b square will obviously remain to the set of real numbers too. So I can say that safely this is a binary operation. So how do you write whether this is a binary operation for your exam? You will write, since the binary operation carries a comma b to a unique element in R. This particular operation is a binary operation. Whenever you are writing an answer, it is always better to follow the steps that are given in your textbook, or still better put, at least try to follow the same kind of writing that is followed in your textbook, so that when you are writing a subjective answer, it becomes more easy for the evaluator to evaluate your answer and to score your answer, right? So, since the binary operation carries the image a comma b to a unique element ab square in R, sorry, my bad, this is a binary operation. So then how will you write something is not a binary operation? To prove something is not true, you only need to give one example. As in the previous sum, the binary operation a binary b was b minus a, which was defined in n. You only need to say that b minus a if b is equal to 3 and a is equal to 5. b minus a equal to 3 minus 5 equal to minus 2 is not an element of n. Therefore, it is not a binary operation. To say something is not true, give just one example. That is enough. But to say something is true, you have to make a general statement. You cannot give examples because you will have to give unlimited number of examples for that. So, make a generalized observation and write it according to the norms that are set in your Cbse book. Right? Now that you know how to check whether a given relation is a binary operation or not, now let us see the property of binary operation, which is commutativity and associativity. Okay, so any operation that is given to you, addition, subtraction, multiplication or division, we always learn to check whether it is commutative and whether it is associative. Now, how do you check whether a given operation, for example, let us take addition. You have two numbers, a and b. When these are added together, we say this operation is commutative if a plus b is equal to b plus a. Okay, and as a rule or as a norm, we always say multiplication and addition is commutative. Okay, so suppose you have multiplication, which is a into b is always equal to b into a, but the same cannot be told about a minus b. A minus b is not equal to b minus a, and a divided by b is not equal to B divided by A. So when we learn about these basic operations, we always learn to check whether they are commutative or associative. Now let us also check. I have explained about the commutativity here of addition, subtraction, multiplication, division, which you obviously know. Now let us learn to check whether a given binary operation is commutative or not. Suppose you have a random binary operation which is given by A binary B, and this binary operation is defined in a set, let us say X. A and B belong to this particular set X. Okay, so this binary operation is defined over a set X and A binary B. This particular binary operation is said to be commutative, which A binary B always should be equal to B binary A. Like we say, A plus B should be equal to B plus A binary B also should be equal to B binary A. Now, depending upon how the binary operation is defined, we need to check if A binary B is equal to B binary A. For example, if the binary operation is defined as A plus B, okay, we need to check whether this particular operation is commutative. Now, you know that A plus B is also equal to B plus A. Why? Addition is commutative. Correct? Therefore, this is equal to B binary A. So, since A binary B is equal to B binary A, I can always say that this particular binary operation, which is given as A plus B, is commutative. Okay. Now, let us check a few more binary operations. We will take a few more examples and check whether they are commutative or not. I am taking a binary operation here. A binary B is equal to A plus 9B. A and B belongs to real numbers. Okay. Now, I have a binary operation here. A binary B defined over real numbers, which is given as A plus 9B. I need to check whether this is commutative or not. What is the condition for commutativity? A binary B should be equal to B binary A. Now, it is given that A binary B is equal to A plus 9B. Now, what is B binary A? B binary A will be equal to B plus 9A. Now, it is very clearly seen that A plus 9B is not equal to B plus 9A, which means that A binary B is not equal to B binary A. Therefore, this particular binary operation is not commutative. Right? Now, let us see the associativity of binary operations. Now, you know that if you have an operation like addition, if A plus B plus C is equal to A plus B plus C, we say that addition is commutative and addition in general is commutative. So, how do you say a binary operation, not commutative, associative. Now, how do you say a binary operation is associative? It is the same. A binary B whole binary C should be equal to A binary B binary C. When A, B and C all belong to the set A, and this is a binary relation which is defined on the set A. Okay. So, whenever you have to check the associativity of a binary operation, this is the condition that you need to check, and I will be doing a couple of examples to check both the commutativity and associativity of given binary operations. Let us now check the commutativity and associativity of this particular binary operation, which is given as A binary B is given as AB by 5, which is defined on Q, which is a set of rational numbers. Now, you know that for commutativity, A binary B has to be equal to B binary A. A binary B is given as AB by 5, which is the same as BA by 5. The reason being multiplication is commutative, which is the same as B binary A. So, since A binary B is equal to B binary A, this given binary operation is commutative. Right? Now, let us check the associativity. Now, for associativity, you know that A binary B, binary C has to be equal to A binary B binary C. What is A binary B? It is AB by 5. AB by 5 binary C will give you, now when I am taking in this form, this is my A now and this is my B now. So, I will get A into B by 5. Right? So, ABC by 25. Right? element. Now let us see what is the RHS. RHS is A binary, B binary, C. So for that, let me first find out what is B binary C. B binary C will give me BC by 5. So when I am doing A binary, B binary C, now this becomes my B and I have an A here. Right? So I get A into B by 5, which is ABC by 25. Now I can see that A binary B binary C is the same as A binary B binary C. So this particular operation, which is this binary operation, which is given by AB by 5, is associative. This is our next binary operation, which is O defined on Q, which is O on Q defined by A of B is equal to A square plus B square for all A comma B belonging to Q. Q means set of rational numbers. So our binary operation is given as A binary B is equal to A square plus B square. I need to examine if this is commutative and if it is associative. Let us first check the commutativity of this binary operation. Now, for commutativity, A binary B has to be equal to B binary A. This is a condition. So, what is A binary B? A binary B is given as A square plus B square, which is the same as B square plus A square. The reason being, addition of numbers is always commutative. This is the same as B binary A. Therefore, this is commutative. Okay. Now, let us check the associativity of the given binary operation. Now, let us check the associativity. Now, what is the condition for associativity of binary operation? A binary B binary C is the same as A binary B binary C. This is the condition. Now, what is A binary B? A square plus B square, right? So, what is A binary B? Binary C. Now, this is my A and this becomes my B, correct? So, this is equal to A square plus B square, the whole square plus C square. The reason being, now this is my A and this is my C. So, A binary B is A square plus B square. So, this binary operation will be equal to A square plus B square, right? So, this is what I am getting. Now, let us see what is the RHS. What is B binary C? B binary C is B square plus C square. Now, what is A binary B binary C? It will be A square plus B square. Correct? You can clearly see that A square plus B square the whole square plus C square is not equal to A square plus B square plus C square the whole square. Therefore, this particular binary operation is not associative. Okay. Now, I hope you are clear with how to check the commutativity and associativity of binary operations. So, now we will move on to the concept of identity element for binary operations. Now, let us move on to a very important topic in binary operation, which is the identity element. Now, what do you mean by an identity element? An identity is something that reflects your own personality. Whatever happens to you, you are your own. You reflect your own personality. Now, in addition, what happens when you add 0 to a number? It does not make any difference to the number. So, basically speaking, the personality or the identity of 3 is not changed when you add 0 to 3. So, I can say that 0 is the identity element for addition. So, what is the identity element for multiplication? All this concept you have already covered in your smaller classes, which is 1. Whichever number you are multiplying with a 1, the identity of the number does not change at all. So, 1 is the identity element for multiplication. Similarly, for a binary operation also, we have something called as an identity element. So, suppose you have a binary operation defined on any element A, and let us say that you have an identity element. Normally, identity element is represented by small letter e. You have an identity element which is existing in the same set as A. So, what is the condition for E to be the identity element? The condition is that for every element A which belongs to this bigger set A, okay, there exists an identity element E which also belongs to a set A in such a way that A binary E is equal to A, which gives me E binary A. So in this same definition of identity element, you need to check the commutativity also. Okay. Let us take an example to get a clear understanding of how to find an identity element and what exactly is an identity element. Okay, now we have the first sum on binary operation in order to find the identity element if it is existing. A binary B is equal to 3AB by 7, which is defined on the set of real numbers. Okay, so I know that A and B belongs to the set of real numbers, and the binary operation result is also defined on the set of real numbers. Now, the condition for identity element is that this particular value of identity, this particular identity element E should belong to real numbers, and the condition is that A binary E should give me A, and this is also equal to E binary A. If I split up these statements, it is A binary E should give me A, and E binary A also should give me A. Right? Now, what is A binary E? Using this binary operation, A binary B is 3AB by 7. So, A binary E will give me 3AE by 7 is equal to A. Okay. Now, from this, can I find the value of E? The value of E from this statement is 7 by 3. A and A gets cancelled. You cross multiply and you get the value of E. Now, let me see whether I am getting the same value of E from this also. E binary A is equal to 3EA by 7. Correct? Fine. This is equal to A. Now, what is the value of E? 7 by 3. In both the cases, I am getting the value of identity element as 7 by 3. Therefore, 7 by 3 is my identity element. Okay. I will explain once again. The condition for the identity element to exist is A binary E is equal to A, which is equal to E binary A. Split it into two statements. This is my first statement, A binary E is equal to A. My second statement is E binary A is equal to A. I wrote what is A binary E from the operation that was given in the question, and I found out the value of E. And using the next statement, E binary A, again I found out the value of E, and both the values are the same. So, E is my identity element, which is equal to 7 by 3. Right? Let us take a question wherein it is impossible to find the identity element, so that you know there are certain cases where the identity element may not exist also. Now, we have our next binary operation, which is A binary B is equal to A minus B. Defined on the set of real numbers. Now, we need to see whether this particular operation has an identity element. So, A binary E is equal to A minus E. It should be equal to A. And E binary A has to be equal to E minus A, which is also equal to A according to the condition for an identity element. So, from the first statement, A binary E is equal to A minus E, which is equal to A. So, what is the value of E? E is equal to 0. From the second statement, E binary A is equal to E minus A, which is equal to A. So, my E is equal to 2A. So, you can see that in both the cases, the value of the identity element do not match. Therefore, this particular binary operation do not have an identity element. So, you need to check both the statements in order to decide whether the given binary operation has a value for the identity element. Okay. Now, let us move on to the invertibility or the inverse element of a binary operation. Now, let us talk about the inverse element of a binary operation. I explained how to find the identity element, and there are cases wherein the identity element for a binary operation may not exist also. Same is the case with an inverse element. Suppose you have a binary operation that is defined on the set A. And let us take it that it has an identity element E, which satisfies this particular condition. Okay. Now, if there is an inverse element B for this particular operation, the condition for B to be an inverse element is that A binary B should give me back the identity element, and that also should be equal to B binary A. This is the condition for an inverse element B to exist. Now, unless we see some examples, just viewing at the condition or just seeing the condition theoretically will not help you understand how B can exist or how B may not exist. So, let us do a couple of sums in order to get the concept more clarified. Okay, so we have our binary operation A binary B given as AB by 5. This particular binary operation, we need to find the inverse element. Sorry, not the identity element. The question is to find the inverse element. So, let us see how to find the inverse element. Now, the condition for inverse element is that A binary B, or let me call the inverse element not by B. Let me call it by something as P. A binary P should give me the identity element. It should be equal to P binary A, where P is my inverse element. Now, if I need to equate A binary P as equal to E as the identity element, I first need to find the identity element. Correct? So, whenever an inverse element is asked, or you have to find the inverse element, our first task is to find the identity element and see if it is existing. If there is no identity element, you can stop doing the sum over there and say there is no identity element, therefore there is no inverse element. Okay? Now, in order to find the identity element, A binary E has to be equal to A, should be equal to E binary A. So, what is A binary E? A binary E is given as AE by 5, that is equal to A. So, I know that E is equal to 5. Right? Now, what is E binary A? E binary A is EA by 5, that is also equal to A. So, my value of E is again equal to 5. So, the identity element, I am getting the same value in both the statements. So, I can say safely that E is my identity element. Now that you have found the identity element, let me go and find the inverse element by substituting the value of the identity element over here. Okay. So, instead of E, I will write 5. So, A binary P should be equal to 5, should be equal to P binary A, where P is my inverse element. Now, what is A binary P? Which is AP by 5 is equal to 5. So, I can say A into P is equal to 24. Okay. Now, in the second case also I get from the first statement, what is the value of P? 25 by A. From the second statement also, the value of P is 25 by A. So, I can say that the value of P is, you are getting the same value which is consistent, right, in both the cases. So, P is equal to 25 by A is my inverse element. But there is a condition over here. What is the condition? The condition is that A cannot be equal to 0. Okay. So, what can I say about the invertibility of this binary operation or the existence of this binary operation? Because this binary operation is particularly defined on Q, which is rational numbers, where 0 is also involved in the group of a set of rational numbers. So, I can say that in this particular case, as long as A is not equal to 0, I can say that this is the inverse element, or in other words, every non-zero element of the set Q, every non-zero element means every value other than 0 is invertible with the inverse element as 25 by A. But if 0 is also included, this particular inverse element does not exist. Okay. So, on this set of rational numbers, there is no consistent inverse element. Otherwise, if you are excluding the value of 0 from the set of rational numbers, say that Q minus 0, then I can say that the value of inverse element is 25 by A. Okay. Okay. Let us move on to the next sum, wherein we will be checking the commutativity, associativity, identity element and the inverse element, their existence for this particular binary operation, which is given as A binary B is equal to LCM of A and B, defined over the set of natural numbers. You have to be very careful when you are checking for the identity element or for associativity. Whatever be the properties on the particular set over which it is defined. In certain cases, you might get the identity element as a 0. You need to understand that 0 does not belong to the set of natural numbers. Hence, that value of the identity element we cannot take the value of the identity element. So, we need to realize that identity element do not exist in that case. So just because you are getting a 0, please do not, when I get an identity element value as a 0, please do not write 0 as the identity element without checking the set over which it is defined. Okay. Now let us start with the commutativity. A binary B has to be equal to B binary A. This is the condition, right? What is A binary B? It's a LCM of A and B, which will be the same as the LCM of B and A, which is B binary A. Therefore, this is commutative. Let us move on to the associativity. A binary B binary C has to be equal to A binary B binary C, and this is the condition. What is A binary B? My LHS gives me LCM of A and B is A binary B. Now what is A binary B binary C? It is LCM of, I'll just break down the steps. A binary B is LCM of A and B. Now A binary B binary C is the LCM of A and B and C. So it is basically LCM of A, B and C. Now what is my RHS? My RHS is A binary B binary C. So what is my B binary C? It is the LCM of B and C. So what is A binary B binary C? It is the LCM of A and LCM of B and C, which is basically the LCM of A, B and C. So my LHS is equal to RHS. So I can say that this particular binary operation is also associative also. Okay. So it is commutative, it is associative. Now we need to find the identity element. Okay. So what is the condition for the identity element? The condition for identity element is A binary E should be equal to A should give me E binary A. We need to break it down into two sentences. This is my first sentence, first statement. What is A binary E? It is a LCM of A and E. This should be equal to A. And what is my second statement? LCM of E and A should be equal to A. Now, if the LCM of A and E should always be A, which means the least common multiple of A and E should always be A irrespective of the value of A, as long as A belongs to the set of rational numbers, what should the value of E be? The value of E should be equal to 1. Okay. What is LCM of E and A? It's the same condition, which is E is equal to 1, and you know that 1 belongs to the set of natural numbers. So my identity element is 1. Okay. Now let us see the invertibility of this binary operation or the inverse element. Okay. Now we know that the identity element for this particular operation is 1. In order to find the inverse element, the condition is, suppose my P is my inverse element. What is A binary P? LCM of A and P has to be equal to 1, or the LCM of P and A has to be equal to 1. Both means the same. So when is the LCM of two numbers equal to 1? When both the numbers are equal to 1. So the value of A and the value of P should be equal to 1. So what do you understand from this? This particular A and P belong to the set of natural numbers, right? It basically means that the value of A equal to 1 basically means that 1 is the only element in this particular set of n which is defined under this binary operation that is invertible, that has an inverse element. There is no other element that has an inverse. Okay. The reason being because the LCM of A and P is 1, which means that both A and P has to be equal to 1, which means that my inverse element and the element for which I am finding the inverse has to be equal to 1. Only then inverse element exists. Every element of the set n cannot be invertible. Only the value of 1 can be invertible. Okay, I hope you have understood this. So we can do one more sum and wind up the lesson on binary operation. And as usual, I am telling you, if you have any doubt, please feel to mail me at the description, at the email ID given below in the description box. Let us do this. AB binary CD, both the sets gives AD plus BC, comma BD. Now, all the elements belong to the set of natural numbers. We will check for the commutativity, associativity, identity element and the inverse element. Okay. Let us start with the commutativity. So, commutativity says that AB binary CD should be equal to CD binary AB, correct? Now, what is AB binary CD? AB binary CD is given as AD plus BC and BD. What is CD binary AB? CD binary AB, according to this, should give me CB plus AD, comma, DB. So, let us start with the LHS and see whether it is same as the RHS. So, AD plus BC, comma, BD is also the same as AD. This is the same as BC plus AD, comma, DB. What is the reason? Reason being addition and multiplication both are commutative. This is the same as CB plus AD, comma, DB, which is the same as what you get in RHS. Therefore, this particular operation is commutative. Now, let us check the associativity. For checking the associativity, AB, binary CD, binary EF. I am taking another element E, comma F. It should be the same as AB binary CD binary EF. Okay. Here I have written down all the steps for proving the associativity of this particular binary operation. So here you can see that I have taken a random element EF over here, and this is a condition for the associativity of the binary operation. So first I need to prove the LHS. LHS is AB binary CD inside the bracket binary EF. So first I did for AB binary CD, it will give me AD plus BC, comma, BD binary EF. When I do that, I apply the same method that is given in the binary operation, which is AD plus BC. Now this is my A, this is my B, this is my C, and this is my D. So this is AD plus BC. So AD means AD plus BC into F plus BC, BD, okay, and BDF. I open the bracket and this is what I am getting. The same logic I have applied for the RHS also. AB binary, CD binary EF. So I need to do CD binary EF. So this is what I get by using this binary operation. And when I am doing it AB binary, this is what I am getting when I open the bracket. So I can see that the LHS is equal to the RHS, and hence this particular binary operation is definitely associative. Now I need to check whether this has got an identity element. I have written down the condition for the identity element to exist. Now I have taken the identity element as E1, comma, E2. The reason I have taken it as a set is because every element involved in this binary operation comes out of a set. So my condition is A, comma, B binary E1, E2. It's the same condition as A binary E is equal to A. Okay. So A1, A, comma, B binary E1, E2 should give me A, comma, B, and E1, E2 binary A, comma, B should give me AB itself. So let me write what is this equal to according to this binary operation. According to this binary operation, A, B binary E1, E2 is equal to AD plus BC should give me A E2 plus B E1, comma, BD. BD is B E2. That should be equal to A, comma, B. Okay. I am equating the elements over here. Okay. So what do I get? I get A E2 plus B E1 is equal to A and B E2 is equal to B. Okay. Now, two unknowns, one unknown. So what do I get the value of E2 as? I get the value of E2 as 1. Substituting this value of E2 over here, I will get A plus B E1 is equal to A. Or I can say B E1 is equal to 0 or E1 is equal to 0. I got the value of E1 and E2 as 0 and 1 by applying the binary operation which is given in the question to this. So, even equal to 0, it is not acceptable, mainly because of the reason that this particular binary operation of ours, when I wrote out the question, if you remember, it was defined on n, set of natural numbers. Since 0 doesn't belong to the set of natural numbers, I can say that this particular binary operation do not have an identity element. Because it does not have an identity element, it also will not have an inverse element. So this particular binary operation is not invertible at all. In this particular class, we learnt about binary operation. We started with the definition of a binary operation, commutativity, associativity, identity element E, and the inverse element. In the definition of a binary operation, we learned that the binary operation has to exist between two elements which we normally represent inside the set. If this belongs to a random set A, the result of this binary operation also has to belong to this random set A in order for this operation to qualify as a binary operation. We also learned that this particular binary operation or any binary operation has to be a function. Then we learned about the commutativity. When we learned about the commutativity, we learned that A binary B has to be equal to B binary A, and for associativity, A binary B binary C has to be equal to A binary B binary C. Then we learned about the identity element E. It may or may not exist. If it is existing, the condition was that A binary E has to be equal to A, has to be equal to E binary A. And this particular identity element has to exist in the same set on which the binary operation is defined. If there is an identity element, we can talk about an inverse element, which says that if P is an inverse element, okay,